All right, let's do section 9.3, page 461, number 13, which reads, show that the two functions grow at the same rate, and our two functions are the natural log of x and the log base 10 here of the square root of x. Now, the first thing that we need to do is to express these two functions as the same type of logarithm, and I think it makes the most sense to express them in terms of a natural log. So I want you to recall, I think it's from chapter 2, that the log base a of x is equal to the natural log of x over the natural log of a. So if we're going to be dealing with the log base 10 of x, then, sorry, not of x, of the square root of x, then this is going to be the natural log of the square root of x divided by the natural log of 10. And I can manipulate this a little bit because remember that this square root of x is really x to the 1/2, and that if I had the natural log of x to the 1/2, I could bring that 1/2 in front, and it would be times the natural log of x, and it would still be over the natural log of 10. And then I can bring this factor of 2 here down into the denominator. So I'm going to have the natural log of x over 2 natural log 10. And remember again that 2 times the natural log of 10 is just going to be a number. So I'm going to be comparing these functions, and I'm going to assign them values. So I'm going to let f of x be equal to the natural log of x, and I'm going to let g of x be equal to the log of the square root of x, which we have rewritten as the natural log of x over 2 natural log 10. So, as you hopefully recall, if I want these two functions to grow at the same rate, then the limit as x goes to infinity of f of x over g of x has to be equal to some kind of non-zero constant. I believe your book calls it L. And so we're going to substitute these functions in and see if we get a non-zero constant. So I've got the limit as x goes to infinity. And for f of x, I've chosen the natural log of x. And for g of x, I've chosen the natural log of x divided by 2 times the natural log of 10. Now, of course, I can simplify this because I have a natural log in the numerator, and I have a natural log in the top or the numerator of the denominator, and I can get those to cancel. And of course, I still have my limit as x goes to infinity, but I've got 1 over 2 natural log 10. And I've still got my limit here as x goes to infinity. And as we all remember, the denominator of a denominator is really a numerator. So this is really the limit of 2 times the natural log of 10. And I don't have any x's anymore. So this is just going to equal a number, 2 times the natural log of 10. So my limit is in fact equal to a non-zero constant. And that tells me that my original two functions up here grow at the same rate.